So one of the most common types of ligands in organometallic chemistry is the carbonyl, right? So this comes from carbon dioxide. So recall the MO diagram from carbon monoxide that we went over in chapter 2, right? Carbon's on the left here, 2s and 2p orbitals. They're higher in energy because carbon's less electronegative, lower ionization energy. Oxygen, 2p and 2s are lower in energy because oxygen is more electronegative, higher ionization energy. And so you get this situation where if you count up the valence electrons, you have these pi star, okay, ligands, antibonding pi orbitals that are the LUMO, the lowest occupied molecular orbital, and then the HOMO, the highest occupied molecular orbital, is this sigma star. And so what can happen is you can have bonding through both of these orbitals occurring. And so you can have a sigma type orbital interaction, right? That's going to be this, you can think about this as like a lone pair, okay, if you're kind of approximating this with the Lewis formulas in, where this lone pair can donate into a d orbital on the metal if it has the right symmetry. But what can also happen is you can have this pi type orbital interaction. We call this pi back bonding because we're getting donation from the metal into the empty pi orbital of pi anti-bonding orbital of carbon monoxide. And so this is a pi interaction, right? Because we have two sets of lobes interacting. You guys are good at that by now. You can draw two resonance structures for this sort of interaction, right? One could be with charge and formally a triple bond, and one could be with neutral and a double bond. But so yeah, you're always going to have this interplay between the sigma type interaction and then the pi back bonding interaction into the LUMO of the carbonyl. So carbon monoxide is not very nucleophilic. I'm just showing these two types of interactions so we remember about them. And so the sigma interaction is actually relatively weak. Remember, nucleophilicity is, how much does something like a nucleus, right? So it's a negative going to a positive in that way. So this is actually relatively weak, and compared to a lot of other complexes where you have these sort of interactions, the energetics tend to line up such that this pi interactions are actually, this pi back bonding is quite important. And so as a result, if you have filled d orbitals, you're not going to form metal carbonyls. So like something like a D10 metal or S and P block metals, right? Because metals without filled d orbitals. So S and P block metals are good examples only, not the D10. Zinc can form carbonyls. So yeah, you need to have some filled d orbitals in order to have this interaction exist, okay, in the first place, right? Because you need electrons here, and so that's just one empirical trend that we can recognize. If you talk to anyone who's into infrared spectroscopy or Raman spectroscopy, vibrational spectroscopy, right? They love carbonyls. Why do they love carbonyls? CO has a very strong stretch, high intensity, it turns out. It has a high vibrational cross section. And with metal carbonyls in organometallic chemistry, it's really nice because you can use their stretching frequencies to identify different types of carbonyls and also look at different trends. So you can see here, as you go across the periodic table in the first row transition metals, the first thing to notice is that free carbonyl, okay, free carbon monoxide, okay, has a 2143 wave numbers is the stretching frequency of that double bond, but all of these values in the metals are less than that, and the reason is because of back bonding, right? So if you have more back bonding, right, you're going to be making this bond, okay, here, this double bond here. So formally it looks more like this if you have a lot of back bonding. And this with a double bond obviously is weaker than this with the triple bond, right? So the more back bonding you have, the weaker your your frequency is going to be, your stretching frequency is going to be, because the weaker your bond is. And so that's why all of these are lower than the free carbon monoxide, okay? But you would kind of think that as you move right on the periodic table, you have more electron-rich metals, right? You're filling them up with more and more electrons, more d electrons, right? So based on that, you would think this trend going from 1976 to 2057, that's going across the periodic table, that the stretching frequency should decrease. But what is also happening here is a competing trend, right? Which is that your atomic orbital energy is decreasing. And why is that? That has to do with ionization energy, right? And so remember, you need the same symmetry, but you also need similar energy in order to get good overlap. And so what ends up happening here is the energetics don't work out as well for pi back bonding for nickel. Okay, so you have less effective pi back bonding for nickel as you do vanadium. And in fact, what you can do is actually use this stretching frequency as a proxy, okay, for how much pi back bonding you have. So if you have something that's very close to 2143, you know you don't have a lot of pi back bonding in that complex, and your resonance structure, you know, looks more like this. Okay, but if you have a much lower, weaker bond, you have this resonance structure with a lot of pi back bonding. All right, the cool thing about carbonyl also is that metal carbonyls have several different binding modes. You may remember when we're doing an 18 electron rule, I had a video all about bridging modes of carbon monoxide and counting counting electrons in those complexes. So you've already seen this a little bit, but yeah, you can bind terminally, you can bind through a bridging way, or you can bind even through three metals bridging, okay? And when you do that, you know, you can see that the carbonyl stretch goes to lower and lower frequencies. The bond is getting weaker and weaker. Why is that? Well, you have more metals donating more pi back bonding, right? 1 versus 2 versus 3. So it's a really nice trend, and you in fact can use infrared spectroscopy to determine, do I have a mu2 bridging species? Do I have a mu3? You can correlate that with crystal structures, right? So it's a really powerful tool for transition metal carbonyls to figure out the structure of these complicated compounds, okay? Here's just some examples of metal carbonyls. Iron pentacarbonyl, very common one. So it's an air-stable orange liquid. You have these this interesting cobalt one, you know, that has these different isomers that can form. There's a black liquid here, a manganese dimer, okay, like a carbon monoxide binding to hemoglobin would be an example. Yeah, this is why carbon monoxide is toxic, okay, because this normally is carrying oxygen, but carbon monoxide forms this metal carbonyl that's a stronger binder than oxygen, which is why, you know, a few ppm carbonyl can be enough to kill you. So you don't want to mess around with, you know, carbon monoxide. Hemoglobin, you know, you need your hemoglobin functioning properly in order to breathe, right? Here's an example of an interesting manganese carbonyl with a methyl cyclopentadienyl ligand. And I learned this when making this slide, that this is used in gasoline. It's an additive to help your engine run better. It's called an anti-knock agent. Back in the old days, they used to use lead. Of course, we found out that we're putting a lot of lead in the atmosphere that was screwing up, you know, people a lot, okay, environmental poison. I don't know how I feel about putting manganese up in the atmosphere. It's a lot better than lead, but I don't know if that's really a great idea. All right, so that's our little survey of metal carbonyls.